All right, so welcome to video 6.6. So we just finished. If you just watched video 6.5, we just finished with an example of lithium nitride, where we talked about how the electron configurations for lithium and nitrogen in the form compound achieve this nice octet, and really that's the driving force for that compound forming in the first place. And we said that the electrons from lithium were transferred directly to nitrogen, which is the basis of an ionic bond. And so just a quick reminder, an ionic bond is where one atom or several atoms transfer electrons to another, creating this electrostatic interaction or attraction between them. And so an ionic bond is very different from a covalent bond in that in an ionic bond, we just have a cation and an anion, and those two things are held together by this positive and negative attraction, which is very different than a covalent bond where electrons are shared between. So ionic versus covalent. And we're going to think about, just in this video, we're going to think mostly about ionic bonds and think about some of the energies that we just learned about, ionization and electron affinity energies, and how and why certain bonds form based on net energy change. And so the example I've got here is for the formation of sodium chloride from their elements. So sodium 0 and chlorine 0. This isn't a real process because, as you've already learned, chlorine doesn't really exist naturally. And sodium doesn't really exist that often, though it's a little bit more common. But this is sort of just an illustration of concept here for a second. So we can start by writing out the electron configuration for sodium 0 from the periodic table. Know that it has that extra 3s1 there. And then we can write the same thing out for chlorine in this case. And we can know right off the bat that because sodium is this group 1a, it's really going to want to dump that electron, right? It wants to get rid of that so that it can achieve this nice noble gas configuration, which means it's going to have a really small first ionization energy. At the same time, we can look at chlorine and we can see that it's coincidentally one electron away from being a noble gas configuration as well. Well, where do you think that one electron is going to come from? Well, it's going to take it from sodium, right? So it's going to add that electron here, and it's going to do that because this has a large negative electron affinity energy, right? And then we can see that in the actual formed compound where the ionic bond has formed, we've got these nice two noble gas configurations that have formed for each of these, or octets, to use the same language that we just learned. So octets are achieved for both of these ions. And the positive and negative nature of these ions after the electron has been transferred gives rise to how this ionic bond forms. So how can we actually think about the two energies involved in this process and think about what the net energy change is in this reaction, right? We know that there's an ionization event, and we also know there's an electron affinity event. So let's write these out. Let's say that the first ionization energy for sodium, that's plus 495.8 kilojoules per mole. So is that favorable or unfavorable to add energy to a system? That's unfavorable, right? We're taking a system and we're adding energy to it to get to a higher state, right? That's an unfavorable step. That's not something the universe really wants to do naturally, so we as humans have to put that energy in to get it to occur. Let's think about the first electron affinity energy for chlorine then. That's going to be minus 348.6 kilojoules per mole. Is that net favorable or unfavorable? Well, that's a release, right? So we get this release of minus 348.6 kilojoules per mole. That's a net gain, right? We're lowering the energy of the system. So we can keep track of these, right? We can just do some accounting. We can add these up, and what we get is a change in energy, a delta E, for this process, which is going to be equal to plus 147.2 kilojoules per mole. So what does that mean? What is if we just account for these two energy steps, would the formation of sodium chloride from its elements be a favorable or an unfavorable process? Well, this is a positive energy, meaning the difference, based on this sort of scale that I've drawn here, is still positive by 147.2. So this is unfavorable, naturally at least, in that some energy from the universe has to go into this system to get this reaction to proceed. But this doesn't account for all of the energies, right? All we've done is account for the electron removal from, or the ionization of sodium, and the electron affinity of chlorine, but we haven't yet at all addressed, well, what is the energy gain or loss through this electrostatic interaction? Right? Is this a good thing? Yeah, the universe likes positive and negative things to be attracted, and so there's some additional energy contribution that we need to factor in addition to these to be able to overall speculate whether that process is favorable or unfavorable. So we just walked through this example of sodium and chlorine in the elemental state and reacting together to form sodium chloride as the ionic solid. And we talked about two different energy terms that we could think about and account for. That was ionization energy of sodium, and then the electron affinity of chlorine to make chloride. And we said that that doesn't give us the full picture, and so we need to develop a new tool set that allows us to think about all the different energies that would go into a hypothetical reaction, and then add them all up and evaluate whether or not it's a favorable or unfavorable process, meaning is it positive energy net or is it negative net energy? And really it's just like putting a spreadsheet together and then adding all the different energies up. We just need to make sure we work through this systematically. That systematic process we call Born Haber cycles, just after the folks that first thought about doing this. And Born Haber cycles, really just accounting for all this energy, are different ways to systematically think about all the steps and the energies required to form an ionic solid. And we're going to do this with the exact same example that we did before with sodium chloride, but we're going to do this and account for all the different energies. Born Haber cycles, it should be noted, don't necessarily and are often not realistic in that they're not the way the compound actually forms in real life. But that doesn't matter, because all we need to do is think about systematically how that compound could form hypothetically, thinking about all the steps, and that will still give us a good sense of whether or not it would be formed favorably or not. And so Born Haber cycles are these energy accounting steps where we think about every step in how that compound can form and add them all up, but we do them in the gas state. And the reason we do that in the gas state is because otherwise we have to account for a whole bunch of complications for things dissolved in solvents and energies that come from solvation of ions. And it gets pretty complicated pretty fast. So Born Haber cycles are the pure thinking about this from only those ions or atoms reacting in the gas state. And so, for example, the Born Haber cycle for the formation of sodium chloride here would hypothetically be sodium ions in the gas state plus chloride ions in the gas state. Even though that's not how they'd actually form, it doesn't matter. It'll still give us the same answer. So we need to walk through this step by step then. The first step here is, and really what we're doing is thinking about what are the elemental forms of the reactants, and how do we get those elemental forms of the reactants into a form that looks like this: sodium ions in gas, chloride ions in gas. And so the elemental forms of sodium and chloride are going to be sodium 0 solid and chlorine gas, Cl2, like this. So how do we take sodium solid and transform that into sodium plus gas, and how do we take chlorine gas, Cl2, and convert that into chloride ion gas? So we're going to walk through each of those steps. We're going to add up all the different energies, and then that will tell us whether or not this compound is favorable or unfavorable to form. So the first step, obviously, is to take sodium metal, sodium solid here, and we need to get that into a gas state. It's in the solid state, so we got to get it to gas state. We call this sublimation, and the sublimation of this compound, or this element, would look like this: sodium solid. It's going to take some energy. We're going to have to heat it up and get it into the gaseous state. And that's going to take positive 107.3 kilojoules for every mole to do that. That's the energy to take solid sodium like this, you know, a cubic little silvery crystal, put some heat into that, and then we're going to end up with some gaseous sodium. Okay, so that's the first step there. So what do we have in the system now? Well, we started with elemental sodium, but now we have sodium gas. We're getting closer to the form that we need for the actual Born Haber cycle, but it's still sodium 0. So obviously we'll have to ionize this in a second. So the second step is to focus on Cl2 gas. Luckily, its physical state is already in the gas form, so we don't need to do anything about that. But we've got Cl2 bound together, right? So it's right now it looks like this. We've got to come in, add some energy, and sever that bond. So we've got to split it in half to make Cl. So what that looks like will be, let's see, grab this pen. That is going to look like 1/2 Cl2 gas is going to split and form a Cl gas atom. The reason that I added a half here to balance this is because, remember, what we're trying to do is take the elemental forms, sodium and Cl2, and make them look exactly like this in the Born Haber cycle. So in that case, I only need one of these Cl atoms in the gas state to get to here. I don't need two. And so I'm going to put a half here, and that's in my system right now. I've got a sodium atom that's gaseous, and I've got a chlorine atom that's gaseous. This is going to take 122 kilojoules per mole. Okay. So as I mentioned, we have sodium in the oxidation state of 0. We need it to get to +1, so we've got to put some energy into the system to ionize the sodium. That's our next step here. So the ionization of sodium is going to look like this. So sodium gas 0. We're going to add some energy. That's going to make sodium ion gas plus an electron. We know this to be the first ionization energy, and that is going to have an energy at +495.8 kilojoules per mole. Okay, so at any step in this process, we want to just identify what do we have in the system, and is it ultimately what we need for our ionic solid formation? The answer is no, not quite. We have now sodium plus in the gas state, so that's good. We have chlorine gas, that's 0-valent chlorine, but we need to get it to chloride. So we need obviously one more step, which has to do with the electron affinity of that chlorine. So step 4 here, up at the top, make some room, that's the chlorine ionization. So we're going to go from chlorine 0 as the atom, and we're going to tack an electron onto that, and that's going to give us chloride atom in the gaseous state. And we know from previous that this is the electron affinity, the first electron affinity of chlorine, and that is going to have a negative 348.6 kilojoule per mole energy associated with it. And we know that, right, because chlorine is not super happy in the 0-valent state. It wants that extra electron because that allows it to achieve that noble gas configuration. So this is a net stabilizing force. This is releasing energy from the system. Okay, so the fifth and final step here then, and this is the one that's new, is the actual energy related to the electrostatic interactions based on the solid formation of sodium chloride. And so we account for this based on what we call the lattice energy. of the system. Lattice energy, or the lattice, is actually referring to the sodium and the chloride and how they form in the crystal. And so we call this the lattice energy, how they sort of arrange themselves infinitely in this network. In the crystal that you actually see and use in your kitchen, it looks like this, but it's really a network of all these ions moving three-dimensionally in space. Okay, so how do we account for this? Well, this is favorable, right? We like this. The universe likes to have these interactions between positive and negative charges, so we can write this out as sodium plus gaseous plus chloride gaseous. Those two things can come together to form sodium chloride solid, and that's going to have an energy of minus 787 kilojoules per mole. Okay, so that is a favorable process. So now what we've done is we've started with pure solid sodium here and pure gaseous chlorine, the elemental forms of these two atoms, or these two substances, and what we finished with was solid sodium chloride. And so the actual overall reaction here, if we added these up, would be sodium solid plus a half of a chlorine gas atom or molecule makes solid sodium chloride. And the reason we can write this as the net overall reaction, we'll write this as net, is because we can go through here, sort of like dimensional analysis, and identify what phases have been used and what haven't. And so we started with sodium solid, and we never actually used that, or we never got rid of it from our expressions. We took sodium gas here, and if you look, sodium gas is here, but then sodium gas is also used here as a reactant. So product side, reactant side, those two cancel each other out if we were to add all of these reactions up together. The same would be true for chlorine gas. It shows up on the product side here and the reactant side here, so those two things go away. The electron here, this is the same electron that gets added to chlorine that was removed from sodium. This is on the product side. Those go away. Chloride gas is also on this side, and our sodium plus gas as a reactant was a product over here. And so if we added all of these things up together, which I'll show you in a second, we would end up having just sodium solid plus a half of chlorine gas and sodium chloride solid. That would be the net reaction, which is the actual elemental reaction, right? And so if we can then add up all of the individual energies for these steps, that will allow us to account for what the overall energy change for this reaction is. Okay, so I've just tallied up all these reactions as I sort of mentioned before, and so we can go back through this and double check that this all works out. So sodium gas on this side, sodium gas on this side can go away. We have chlorine gas and chlorine gas here. We have this electron and this electron. We have chloride gas, and then we have sodium plus gas and sodium plus gas. And so the net reaction here is sodium plus half a chlorine molecule gas makes the solid NaCl. Also, sort of by convention then, we can go through and add up all of these individual steps here. It's just, I would take the time to pause the video, make sure you get the same answer as me, and that yields this number, minus 411 kilojoules per mole. Remember, minus or negative energies mean energy has to leave the system, and we're going from a higher energy state to a lower energy state, which is good. The universe likes that, so this is a net favorable interaction. Let's do this graphically here for a second. So I'm going to pause the video. I'm going to draw this up, and then you'll see how we account for this graphically. Sometimes it's helpful to do that too, and sometimes I'll ask you to do that. Okay, so I've drawn this up graphically now. So what I've done is I started here. Let me draw this. So I start here. Doesn't matter. You start in an arbitrary point. You draw your line there, and at that point, this is the elemental forms of the compound you ultimately want to form. So this would be sodium, metal, sodium 0 plus half a chlorine. That's where we're starting. So we've got the elemental forms by themselves, not combined at all. And then down here, the final point we'll get to is the actual compound that you're aiming for. Okay, so we take that sodium solid, right, and the first thing we do is we turn it into a gas, which is this first step, which is step 1, so sodium solid to a gas. That requires 107.3 kilojoules of energy. And at that point, we've converted everything into sodium gas. We do the same thing for, or not the same thing, but we have to cut the chlorine molecule in half and get chlorine atom because we have it in a molecule form, and that's going to take 122 kilojoules of energy. I didn't mention this before, but we call this bond dissociation energy because we're actually breaking the bond. So you may hear me talk about that. We will talk about it in greater detail later, but I just want to add that in here. So we break that bond in step 2, and then we got to ionize the sodium metal, and that's going to take 495.8 kilojoules per mole. And so I'm just adding energy. So up at this point, we could just think about what do we have in the system at the top of this line here. Well, we've got sodium plus gas. We've converted our sodium solid into sodium plus gas, and we have chlorine 0 as a gas. So we're not quite there yet, but that's where we are at the top of the hill. What we then see is to get chlorine to chloride, we tack an electron on. That's a net good thing. That's that minus 348.6 in step 4. So we actually start to descend here. And then we've got, at this point in the diagram, we've got sodium plus gas and chloride minus gas. And so if we allow those two things to come together, we need to invoke the lattice energy here, which is net stabilizing. That's step 5, and it's hugely stabilizing. Look at the size of the electrostatic interaction relative to some of these other smaller steps. And so it's this difference then, this big blue arrow here, that's the difference from the starting point of the elements in their natural state, how we'd find sodium and chlorine, to how we would have the ionic compound of sodium chloride. And so the sort of takeaway here is that sodium chloride is a good thing. The reason we have it, and the reason we eat it, and the reason it's so stable is because it's way more stable by about 411 kilojoules per mole than the original atoms or elements themselves. And so the Born Haber cycle, this whole thing that we just walked through is a Born Haber cycle, which is just an accounting mechanism to keep track of all the energies of all the steps to ultimately think about the formation of this ionic bond. Okay, so I've got an example here. This is a type of example you'd expect to see on a graded workshop or an exam, where I'm going to ask you to calculate the overall energy change for the formation of a solid. In this case, it's this ionic compound, potassium fluoride, and then I might ask you to draw the actual graphical Born Haber cycle. So exactly what we just did, but with a different solid. In that case, I'd give you a table of values like this. So we've got the heat of sublimation of potassium solid, so that's the energy required to turn solid potassium into gaseous potassium. Bond dissociation energy of fluorine gas, so that's splitting that bond, just like we did for Cl2 before. The lattice energy is that energy that you get from the electrostatic attraction of potassium ion and fluoride ion. E sub Ea, that's the electron affinity of fluorine atom. So when you tack an electron onto it, what do you get? And then E sub I, that's the ionization energy of the potassium metal. So I'd pause the video now, and start working through this. When you unpause it, you'll see my worked example, and I'll walk you through what I did. Okay, so the first thing that we want to do is just write out what this reaction would look like from its elemental state. And so the elemental form of potassium is just potassium solid. The elemental form of fluorine, we know it actually prefers to be a diatomic because it's a group 7, so that would be plus fluorine. To get this thing to balance, we only need a half of that, just like we did for NaCl. And so this would be the balanced sort of elemental reaction that we're trying to get to. So that means how do we actually form this solid? Well, we need to get potassium into the gaseous state, and so we're starting here again. I just chose some arbitrary point. This is the dark black line, so start here. We take potassium and we convert it into gaseous potassium. That takes 89.2 kilojoules per mole. That's what we got from here. We do the same thing for fluorine that we did before with chlorine. So we have that bond dissociation energy, so we use that to split it in half. It's important. In the previous one I didn't mention this explicitly, but I want to be really clear here. When you're given a bond dissociation energy for fluorine gas, that's the bond dissociation energy to take that whole molecule of fluorine and sever it in half. That would produce, that would take you from fluorine to 2 fluorine gas atoms. But we only need one of those in our actual reaction, right? And so I only need half of that energy in my accounting. So I'm going to put this little half here because I'm only accounting for half of a fluorine molecule in my reaction here. So that's a half. That's a really important thing. This comes up almost every time we do a Born Haber cycle, but it's also the place that can be kind of tricky if you forget. This is almost always going to be true. Okay, so at this point we've got 2 gaseous atoms, but no ions yet. So we need to ionize the potassium gas. That's going to require 418.8 kilojoules per mole, which comes from the first ionization energy of potassium. At this point, at the top of this black line, what we have are potassium ion in gas form, and we have fluorine 0 as a gas. Right? They're not quite there yet. Now we need to ionize fluorine. We do that through the electron affinity. It likes that because it's going to form an octet. That liberates 328 kilojoules per mole, so we start to go down in energy, which is good. And now at this point here, we've got fluorine ion and we've got potassium ion, both in gas form. And so we're going to allow those two to come together via this lattice energy. That's always a net gain because you have electrostatic attraction between those positive and negative ions. That's going to give you a huge bump, 821 kilojoules per mole in the negative direction. And so we're comparing, right, where this intersects, because starting here, that was starting with potassium solid and fluorine gas. So the elemental forms that we'd find in the natural world, that's where we started in energy, and where we ended was actually lower than where we started, this down here being the energy of potassium fluoride. And so it's this net difference here that gives us the change in overall energy, which was what we were asking for. So delta E is the same as the change in overall energy. So that change in overall energy here is equal to minus 562 kilojoules per mole. So if you didn't already, I would walk through this, make sure you get the same numbers that I get. This is almost certainly going to come up in some way. You'll be asked to do this as a group or individually or both. I could ask you something like this, or I could ask you something a little bit with a little bit of a curveball, where maybe I give you in your table, I give you all these values, but maybe I throw in some extra values that you don't actually need. So maybe I give you say also EI2 of K, right? That would be used to make K2 plus, which we know doesn't like to form because that breaks the octet, and it's also not the oxidation state in KF in the final compound. So you don't actually need to use that. but it may feel like you need to use every parameter, and that's not the case. I may throw a curveball like that or something similar. Another question I could get at is I could give you, in this table of values, I could give you the actual overall delta E. I could give you minus 562 in this case, in this example, but maybe I don't give you the lattice energy. So maybe I give you everything except the lattice energy, including the computed overall, and then I ask you to actually compute this value, the minus 821. No different. You just have to set up this value and then evaluate what this number would be to give you a total energy change of minus 562. So either way, these are the types of questions that would be in the back of your book, or maybe in a workshop, or a quiz, or an exam. So make sure you practice these a couple times.